All right, hello everybody. So now we're going to talk about section 2, which deals with a large sample test about a population mean. Now we know large samples are anything n greater than or equal to 30, okay? So the idea behind it here is this, and I kind of just wrote some notes down while I was thinking about how I wanted to approach this section here, is first, x bar is going to be the best estimate of the actual population mean mu. So if we assume, for example, that mu is equal to some number, if we assume that mu is true, or that the null hypothesis is true, then our sample statistic, in other words, all the data that we've collected when we calculate x bar, it should be relatively close to the population mean. Now, I use close in quotation marks because, what does that mean to be close? I mean, if you're talking about dollars, $1 is nowhere near the same as, $1 million. However, if you talk about $1 million and $1.5 million, well, those are kind of close to each other. There's a difference of only 500,000 there. So this idea of close is relative. So what we do to kind of help us with that, and I have a picture here drawn, which is just something that's normally distributed, and I'll zoom in here for us. So if mu is right down the middle, and we know x bar is going to be some distance away from mu, well, that's nothing more than just the z-score. So the question becomes, that distance, is it statistically significant or statistically not significant? So this is the question that we're going to be asking ourselves. Is it statistically significant? Okay? Now, in order for us to do that, we have what we call a test statistic. And the idea behind this is, and if you think about it, if x bar, and let's say, I'm going to draw something right here. I'm going to draw it in red for us. So in the previous lecture video, we learned the differences between the critical region and then the non-critical region. Excuse me, in other words, in our critical region, we reject the null. And then in our non-critical region, we fail to reject the null. So if my x bar distance away from the mean is right there, which is a z-score, okay? Notice here, we would fail to reject the null hypothesis, meaning that we're assuming that this relationship is actually true. We cannot reject the null. However, and you'll have to excuse me here, if my x bar value is inside that rejection region, then I know the difference between mu and x bar, so the difference between this distance right here, is actually statistically significant, meaning that HA, your alternative hypothesis, may be true. Now, the crazy part about this is that you do not automatically assume the alternative is true. Okay, you can't just automatically assume that. But what you can say here is, I have enough evidence to reject the null hypothesis, which means the sample data that I've collected support this alternative hypothesis. The best way is to do this experiment over and over again and get more data samples, and then you have a strong case of saying, yes, this alternative hypothesis is true. All right? So let me just reiterate that. Just because you can reject the null, you can't automatically assume that the alternative is true. It's just, it's not this. It's not the null, which is a good thing. That means you got something that is statistically significant. It doesn't just happen by chance. So I think the best thing that we can do now is kind of look at a problem and just see, okay, well, how do we actually do, or how do we conduct an hypothesis test? So I got a little example here. You don't have to worry about data set 2, all right, because the information is summarized for us. However, I'm going to go ahead and read this. So in data set 2 in Appendix B, which comes from a different book, it includes 106 body temperatures with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. use a 0.05 significance level to test the claim that the mean body temperature is less than 98.6 degrees Fahrenheit. And then we're going to answer the question, based on these results, does it appear that the commonly used mean of 98.6 degrees Fahrenheit is wrong? So let me give you a little bit of background on this problem. Number one, we have a very large sample size. We have 106 body temperatures. So off to the right here, I'm just going to write n equals 106. Second, of the 106 body temperatures, we know that they have a mean of 98.2. So x bar equals 98.2 degrees Fahrenheit. And we know the standard deviation is 0.62 degrees Fahrenheit. Now, a long time ago, we've developed ways to measure the temperature of our body. It just so happens, though, that we haven't really changed. So you and I both know that we say if you take your temperature to 98.6 degrees Fahrenheit, then that means you do not have a fever or you don't have a cold or anything like that. Your body's normal temperature. However, somebody went ahead and got 106 people, tested their body temperatures, and found that it's not actually 98.6. It's 98.2. So then this researcher made a claim. And their claim was, and I'm going to highlight the claim here for us. They made this claim that says the mean body temperature is actually less than 98.6. So I know this is a really simple or silly example, but in a way it's so profound in what we're actually doing here. Because if you think about what's happening, we've gone our whole lives thinking 98.6 was normal. One researcher tested that and said, well, if you're going to tell me it's 98.6, I'm going to actually do my own research. I'm going to get 106 body temperatures, and what I found was it's actually less. So what we're going to do is we're going to test to determine, is this difference between 98.6, so I'm going to write that over here to the right, is the difference between 98.6 degrees Fahrenheit and 98.2 degrees Fahrenheit statistically significant? Okay, because if it is statistically significant, we've been lied to our whole life. But if it's not statistically significant, then, the 106 body temperatures that we found it's not enough to reject the null hypothesis, which means there is no difference between 98.2 and 98.6. They're basically the same temperature. Okay? So how do we actually do this? Step one, we identify our null hypothesis. So our null hypothesis always contains two things: the population parameter and the equal sign. So since we're talking about average body temperature, our population parameter is going to be mu, and that has to equal 98.6 degrees Fahrenheit, because that is what we've been told our whole life. Okay? Second is going to be the alternative hypothesis. Now remember, the alternative hypothesis contains less than, greater than, or not equal to. Okay? And you're going to look for keywords. So keywords would be obviously less than, okay, or maybe smaller. Let me zoom in for us here. The greater than symbol, obviously it's going to be greater than. Okay? The only one you really got to be concerned with here is the not equal to symbol. A good word for not equal to is going to be different. Okay? It's going to be different. Now, there is a reason why we have to know them. The alternative hypothesis helps us to graph. And I'll show you what that looks like in a little bit, okay? So our alternative hypothesis comes from the problem, and in fact, it's already highlighted in that purple color. Maybe I shouldn't use that purple color. Maybe I'll use a different color. But we'll use blue. I like blue. So if you read this problem right here, in the blue it says less than right there. So I know my alternative hypothesis is going to be mu is less than 98.6 degrees Fahrenheit. Now, this is just me, all right? I like to just kind of condense my information. So directly underneath here, I'm just going to write the null, mu equals 98.6, and then the alternative, mu is less than 98.6, okay? So now we need to find our test statistic, and this is going to be a formula. And I have it right up here at the top of your screen, and that test statistic tells me the distance that mu is from the observed data that we've collected, okay? Or better yet, let me say it this way. The test statistic tells us how far away or the distance between the test statistic that we've calculated, the data that we've collected, from mu. I think that's a better way to say it. So our test statistic, z equals x bar minus mu over s divided by the square root of n. Now, if we have a large sample size, actually, let me write it like this. We'll use sigma over the square root of n. However, if n is large, meaning n is greater than or equal to 30, then we can use the test statistic z equals x bar minus mu all over s divided by the square root of n. So I'm going to make sure that we have large sample sizes because that's what this section is all about. In chapter 10 is when we focus on small sample sizes. So here we go, test statistic time. Z equals, now, in the upper right-hand side of your screen, there is our information from the data that we've collected. So Z is going to equal 98.2 minus 98.6, all divided by 0.62 over the square root of 106. All right, so when you calculate this, and the hardest part about this, honestly, is just typing it into your calculator correctly. Make sure that when you're doing that, you're putting, make sure when you're doing this, you're putting both of these in parentheses, okay? I've seen too many times we just don't know how to use our calculator properly. If it works or if it helps, do little individual calculations and then go ahead and find the total. But when we do the calculations here, I'm going to round to 2 decimal places. We get negative 6.64. Okay, now, what does this all mean? Well, that's where step 4 kicks in. So step 4, we're going to label our rejection region. Okay? So here's what we have. We have something that's normally distributed, okay? Because we know we have a large sample size. Central limit theorem tells us that the larger the sample size, it's going to approximate a normal distribution. So this is okay. Now, we know that our hypotheses, mu equals 98.6. The alternative, mu is less than 98.6. So according to the alternative hypothesis here, okay, we have a left tail test. Remember, I went over that in the first video. So this is going to be a left tail test. Now, I know this is my rejection region. And what we're talking about is reject the null. This is going to be my fail to reject region. The question becomes, how do we find that number right there? And that number comes from our level of significance here, alpha. Now remember, in the previous video, alpha is the amount that I am willing to be incorrect. So in other words, in this case, the problem asked us to use a 0.05 significance level, okay? So I'm going to write that down, 0.05. And here's basically what this number represents. If I were to conduct this experiment 100 times, so if I were to conduct this experiment 100 times, I would successfully conclude the correct answer 95 out of 100 times. That's what 0.05 stands for, okay? Because if you think about it, it's like 5%. I'm willing to be incorrect 5% of the time. 95%, I know I'm going to be correct. You got to remember, nothing is perfect. So you got to have some sort of leniency here. So when I see a level of significance of 0.05, that is telling me that I'm willing to be correct 95 times out of 100, or 95% of the times I'm willing to be correct. 5% of the time I'm willing to be incorrect. And because we have this level of significance of 0.05, this helps us to determine our critical value. Now, we need to go all the way back to chapter 7. To be honest with you, I think we need to go all the way back to chapter 6. Because we know, since this is a normal distribution, the area under the curve is equal to 1. Which means, if I am willing to be incorrect 0.05 of the time, that is the area of this rejection region right here. Okay? So, what I'm going to do is I'm going to find in my z-score table an area of 0.05, because you got to remember, if mu is the population mean right down the middle, what I'm going to find is this distance right here that separates my rejection region from my fail to reject region. So let me go ahead and get our z-score table out, and I'm going to show you how to do this, okay? Because that's going to give us our critical value. All right, I'm back, and here I have my z-score table, okay? So notice here that the picture we drew in our notes is very similar to this up in the upper right-hand corner. And like I said, what we need to find is that z-score. So if you scan in the body of the table, remember the body of the table, I don't want to use this color anymore. The body of the table are area values. Okay? We need to find alpha equals 0.05, or as close as we can. So if you scan the table from left to right, and I know there's a lot of numbers. Right here is a little asterisk. Okay? And if you follow that down, all right, it's going to say area is 0.05. And if you notice to the right or to the left of that, that means it is a z-score of negative 1.645. And that is our critical value. The critical values, for the most part, are generally the same. However, they are different depending upon what your alternative hypothesis is. So you've got to be careful. So let's go back into our notes here. And we're going to label that rejection region of negative 1.645. Okay? So what does this mean in terms of our test statistic that we calculated? Well, our test statistic was negative 6.64. And when you compare negative 6.64 to negative 1.645, negative 6 is all the way in here. I mean, it's to the left of negative 1.6, which means we are now in the rejection region. So, excuse me. So I'm just going to write one simple statement. Since negative 6 point, I even forget what it is now, 64 is in our reject the null region. Better, let me write it like this. It's in our rejection region, comma, we reject, I'm going to write it nice and large and underline it. We reject the null hypothesis. Okay? Now, let me write our null hypothesis and the alternative hypothesis again so we can see what's happening here. Because I want us to understand what just happened. All right, so since we can reject the null, we know that the sample data supports the claim that, and I'm going to write that, the sample data supports the claim that the mean body temperature is less than 98.6 degrees Fahrenheit. So that's all this is saying here. Okay? And when you think about it, it's actually very powerful right there. Because like I said, our whole life we've been told normal body temperature is 98.6. However, the data that we've collected actually supports the claim that it's actually less than that. Okay? Now, just because our X bar, just because our mean was 98.2, does not imply that the average body temperature is actually 98.2. It does not imply that at all. It just means maybe the actual body temperature is less than 98.6. Now, here's the most amazing part about what we're learning and how it all fits in. We know, according to the data we've collected, that the actual body temperature, according to the data we've collected, that's so important that we say that, is less than 98.6, okay? Maybe a good way to figure out, okay, well, what is the actual body temperature then? Is to estimate what the body temperature is by creating a confidence interval and then giving some sort of confidence. I'm 95% sure that the true mean body temperature is in between these two numbers. And the more data you get, the tighter or smaller that range is going to be. In fact, I literally just Googled this right now. If you go to, and this is what I go to, I'll show you. What is average body temperature? And I clicked on this right here. And the only reason why I clicked on this is because it's from May 15th, 2021. And this is the main article, but this is just a reference to it. So within the first, let me zoom in here so we can read it. Within the first couple paragraphs, not everyone's normal body temperature is the same. Yours could be a whole degree different from someone else's. German doctor in the 19th century set the standard at 98.6, but more recent studies say the baseline for most people is closer to 98.2. In fact, for a typical adult, body temperature can be anywhere between 97 and 99 degrees Fahrenheit, with babies and children even a little bit higher than that, or a little bit more of a range, okay? So, and there's all these different things that actually contribute to that. How active you are, time of day, your age, sex, what food have you eaten, where you are in a menstrual cycle. I mean, all these different variables contribute to this. So, this is how important our statistical studies really are, which is if somebody makes a claim, we're going to test it. We're going to see, okay, is there a difference or is there not? All right. So hopefully with this just little silly example, and maybe with how fast I'm talking, and hopefully you can feel the passion behind my voice here, you could see just how important this is, and more importantly, how much fun I have doing this, because finally, it's one of those things where if somebody says something and you sit there and question it just for 1 second, now you have a scientific approach on how to determine, is what they're saying, does it hold weight, or is it just all fluff? What I want to do now is just use this again, okay? And I want us to do a couple more examples using this approach, okay? Then we're going to look at some examples using the p-value approach. And I'm going to come back and reference this one when we do the p-value approach. So give me a second. I'm going to just copy and paste another example into our notes. Okay, I'm back, and here's our next example here. So another one, it's pretty simple, but I want to go over this because the alternative hypothesis is different in this situation. So in previous tests, baseballs were dropped 24 feet onto a concrete surface, and they bounced an average of 92.84 inches. In a test of sample size 40 new balls, the bounce heights had a mean of 92.67 inches and a standard deviation of 1.79 inches. And this data was based on somewhere from the Brookhaven National Laboratory. I have no idea where that is. Use a 0.05 significance level to determine whether there is sufficient evidence to support the claim that the new balls have bounce heights with a mean different from 92.84. And then we're going to answer the question, does it appear that the new baseballs are different? Okay? So once again, I'm just going to kind of go through the problem and let's highlight the important information here. First, we got a sample size of 40 baseballs. So I think that's pretty important. So I'm just going to write n equals 40. We know their bounce mean is 92.67. So x bar is going to equal 92.67 inches. And then the standard deviation is going to be 1.79 inches, okay? And I'm also going to just highlight, I think, what a very important part of the problem is, which is somebody's claiming something. So the claim is that the new balls have bounce heights with a mean different from 98.2 inches. All right, so let's get to the good stuff. Step 1. Let's identify the null hypothesis. So remember, the null hypothesis is going to have our population parameter mu equal to some number. Well, in this case, in previous tests, baseballs were dropped from 24 feet onto a concrete surface, and they bounced an average of 98 or 92.84 inches. So that is going to be the population mean, because this is all the previous testing. So that's what we're going to compare this to. 92.84. Step 2 is going to be our alternative hypothesis. Now remember, population mean is going to be the same, and the number is going to be the same. The only difference here is, what is the symbol in between? Well, if you read the claim, we see the keyword different. So this is going to be not equal to. All right? Now, step 3. Step 3, we're going to calculate our test statistic. And notice with this example, you could see just how more condensed my information is, because now that we have an idea on how to do this and we understand the process, this actually goes very quickly. Okay? So our test statistic Z is going to equal x bar minus mu all over S divided by the square root of n. So Z is going to equal x bar 92.67 inches minus 92.84 inches divided by 1.79 over the square root of 40. And when I use my calculator here, I come up with negative 0.600, but z-scores, we rounded just 2 decimal places here. So we're just going to keep it as negative 0.60, okay? Now, step 4. Step 4 is the biggie. This is where, and I'm going to go ahead and just say rejection region, graph, and critical value. Okay? So, remember, earlier in the problem, they said to use a 0.05 significance level. So, alpha equals 0.05. Now, you got to remember, this number represents the total area in the rejection region. Okay? Now, the reason why I'm really emphasizing this here is because when we go ahead and we do our graph, In the previous video, when I went over the differences between the hypothesis or the alternative and like what it looks like, if your alternative hypothesis is not equal to, that is a two-tailed test. Now, let's highlight our rejection regions. So this is reject the null, and this is reject the null. But here's the catch. Alpha equals 0.05 is going to be the area in the rejection regions. So we have two regions here, which means since I have two of them, the area in this is going to be 0.05 divided by 2, and the area here is going to be 0.05 divided by 2. And when you take 0.05 and you divide it by 2, you get 0.025. So that is the number you have to look up in the body of your table. You do not look up 0.05. You got to look up 0.025 because you have what we call a two-tailed test. All right? That is crucial that you understand that. Now, what's nice about this is since this is a normal distribution and it's symmetric, if you find the critical value, so let me kind of clean things up here. So once you find the critical value to the left, all you got to do is just find the critical value to the right by making it positive. Because remember, right down the middle, technically, is mu. So anything to the left is going to be negative, anything to the right is going to be positive. So let's go back to our table and we're going to find 0.025. All right, so here we go. Let's erase some stuff. All right. So we need alpha 0.025, okay? So, excuse me. So I'm going to go ahead and just scan. And I only know this because I've done this so many times. But right there, I can zoom in somewhat, is 0.0250. And if you look at the critical value, it's going to be negative 1.96. Therefore, our left rejection region is going to be negative 1.96, or the critical value. And the critical value for the right rejection region is going to be positive 1.96. Okay? We also know right down the middle, or in the middle of this graph here, is our fail to reject the null region. So what I'm going to do now is I'm going to go ahead and take our critical value, which is negative 0.60. Think about where does that fall on this horizontal axis. It just so happens it's like over there somewhere. If you want to, you can write Z test. That's fine with me. Or you could just literally just write an X and call it a day. That's fine. Because the most important part here is our conclusion. All right. And what we're going to do is we're going to write a statement. So since negative what was it again? 0.60 is in our fail to reject region, we conclude that, and here's the best part, all right? You cannot reject the null, which means we conclude that the difference in bounce heights of the new ball and the old ball is not significant. So you may have like a baseball manager that comes out and says, these new baseballs are horrible because they bounce too much. So then they call the math people in. And here's what we do. We do our math and we say, hey, Mr. Baseball Manager, I'm very sorry, but the difference in heights is not significant. You guys just, you're no good. Your hitters are bad, or your fielders are bad, or whatever the case may be. Okay? So I hope this is like kind of making sense. All right? Now, I want to go ahead and talk about this p-value thing, okay? Because this is another way. In fact, if I go back to the notes from the previous lecture here, all right, so let me look right here in the notes. I'm going to block it in. We have two ways that we can actually do hypothesis testing. The first is a test statistic, testing population means. That's what we're currently doing, okay? Some people refer to this as the classical method. All right? Now, there is another method called the p-value method. Now, normally with the p-value method, we like to use technology, okay? However, you can still use your table when using the p-value method. So let me show you how the p-value method works. So the p-value method is a comparison of, and I'm going to write it down here, the p-value that we calculate and alpha. And basically, there's an easy way to remember this. And it's if, I was already going to write the table here. If the p is low, then the null must go. Okay? Meaning, if the p-value is less than or equal to your level of significance, you're going to reject the null hypothesis. Otherwise, if the p-value is greater than alpha, you're going to fail to reject the null hypothesis. So this is just another way that we can do it. And to be honest with you, if you were going on for like, you know, a master's degree or something like that, and you talk to, let's say you're doing your research project, and I would imagine you would go talk to the math lab because, you know, I mean, it is daunting to collect all this data and try to remember every little detail that you and I went over in class. And to be honest with you, unless you're going for a degree in mathematics, we're not really concerned with the process on how you actually calculated every little number when you type up your research report. What we want to know are, what are the results? How do you interpret them? Okay? So if you were to talk to like a math lab person, they're going to be doing the p-value method because you got a calculator or you got a computer in front of you. But let me show you how this works. So we're going to go back to the first problem here. All right? So we've already established that we're rejecting the null hypothesis. So when we do the p-value method, we should come up with the same exact result. And here's how we do this, okay? Our test statistic turned out to be negative 6.64, if I remember correctly. I just got to find it real quick. Where are you? Yep. Okay, so our test statistic turned out to be negative 6.04. The question becomes, what is this area inside the body of the z-score table? Like, remember, this test statistic is a measure away from the mean. It's a z-score. So if I were to take my table and try to find, now remember, I'm going to write it up top here, z equals negative 6.64. Notice that very first thing it says, hey, listen, if you got negative 3.5 or lower, which means to the left, just use 0.0001 for an area. So that's what I'm going to do. So my p-value is 0.0001. Now, my level of significance for this problem was 0.5. And when you compare these two numbers, notice that our p-value is definitely lower than 0.05. Now, because we know our p-value is lower than 0.05, We just reject the null hypothesis. And that's because we know the p-value is going to be contained inside that rejection region. Because remember, the rejection region is the area under the curve. And we're at 0.0001, which is so far to the left. Okay? So some of you may be asking yourself, well, if you told us we can use the p-value method with technology, why did you use the table? Well, number one, I use the table because the table is really easy. It's readily available. And then I can show you this using technology if you want. And I'm going to do it right now, okay? The thing you got to remember here is your values when you use technology are going to be maybe a little bit different. And that's because, like I said earlier, technology keeps all the decimal places. And in fact, in chapter 10, we're going to learn this thing called the student t distribution. I don't want to go too far into it now, but that's what SALT is going to be using. So let me just show you how to do this inside of SALT. So there we go. So on the left-hand side, you're going to want to select one sample t. Okay, that's all you got to worry about is one sample t, and it's already selected. Then we're going to type in the information from our problem. So our sample mean, 98.6. The sample deviation is, what was it again? 0.62. The sample size was 106. We want to click on hypothesis test, which it's already there. The hypothesized mean, that is your null hypothesis. So for the body temperatures, it was 98.6. And then the alternative hypothesis, in our case, was less than. So when I click on generate results, notice you get your summary. But the most important thing that you want to look at is going to be the p-value. Uh-oh. Did I type in something incorrectly? Oh, I did type in something incorrectly. Oh, I feel so dumb. I'm so sorry about that, everybody. I put 98.6. Fat fingers got in the way. It's supposed to be 98.2. So now everything's normal. Let's generate the results. Here we go. N equals 106. Our mean is 98.2. Sample standard deviation is 0.62. Even look above. It gives you the null hypothesis. It gives you the alternative hypothesis. You do not have to worry about standard error or degrees of freedom. So these two middle things, you don't have to worry about this. You will worry about it in chapter 10. But most importantly, look at our test statistic. Negative 6.64, which is exactly what we calculated. And look at our p-value. Our p-value, what this is telling you is it is smaller than 0.00001. It's so small. So when you compare that number to 0.05, obviously you're going to reject the null hypothesis. Let's go back to our notes because I want to do the same exact thing again. Except I want to do it with this problem right here. And hopefully I type in the right information again. All right. So let's go ahead. Where did I want to write this at? I'll write it underneath here. So for the p-value method, all right, remember our level of significance, alpha, in this case equaled 0.05. That's the total area. That's what we're concerned with, okay? So I'm going to write 0.05. And we know that our test statistic turned out to be negative 0.60. Now, this is just a really nice number. We got really lucky with this, okay? Because what we can do is, like I said, we can go back into our table. Negative 0.60. And when we go ahead and try to find that on our table, here's negative 0.60 is right here. So that is 0.2743 in terms of a p-value. So our p-value is 0.2743. Is that correct? Let me just look at it one more time. 0.2743. Good. So now when you compare these two numbers, 0.2743 and 0.05. 0.27 is larger than 0.05, which is, and I'm going to highlight it for so you can see exactly where I'm talking about, which is right here. Our p-value is larger than our level of significance, so we fail to reject the null. And if you go and you look at the graph that you created so beautifully, notice your test statistic was in the fail to reject region. Now, if you wanted to use technology, okay, and I just need this real quick. So we're going to go back over. We're going to reset everything. Remember, leave it as one sample t. Our sample mean is going to be 92.67. The sample deviation was 1.79. The number of samples is 40. We want a hypothesis test. The hypothesized mean is 92.84. And our alternative hypothesis, remember, was not equal to. So we're going to click on Generate Results. And now, you can see here, we got n equals 40. Our mean is 92.7. Deviation's 1.79. The null and alternative hypotheses are labeled for us. Our test statistic is exactly what we calculated, negative 0.60. The only difference here is that p-value. Now, I'm telling you, you're going to get different values here, but you need to use analytical skills, okay? What I'm really concerned with is if you're going to use technology to find your p-value, and I'm cool with that, okay? Make sure that your test statistic is the same exact value as what you collected. Now, they're saying this is a t-test statistic. We are calculating z-test statistics. I don't care about that. It's the value that we're concerned with. Now, our p-value here is going to be 0.55. So I'm going to go ahead and copy that down into our notes, all right? Oops, I need to change my marker. So using tech, we got a p-value of 0.55, which is still greater than 0.05. And that's really all I'm concerned with is what is the conclusion, okay? Once we hit chapter 10, you're going to see how this changes a little bit. Right now, I got to be honest with you, when we're talking about a large sample test about a population mean, it's almost as if everything was perfect. Like chapter 9, we're living in a perfect world. And you and I both know we do not live in a perfect world. So the question becomes, well, if we don't live in a perfect world, how do we do it? That's chapter 10 for us, okay? So I want to go ahead and do just one more problem. So give me a second here. I'm going to copy and paste it. And I'm going to do it the same way. I'll do it the classical approach, and then I'll show you the p-value method. All right, so here's our last example, what it deals with Everglade temperatures. So in order to monitor the ecological health of the Florida Everglades, various measurements are recorded at different times. The bottom temperatures are recorded at the Garfield Bright Station, and the mean of, geez, that doesn't even make sense. Did I even read that correctly? Are recorded at the Garfield Bight Station, and the mean of 30.377 degrees Celsius is obtained for 61 temperatures recorded on 61 different days. That sentence is horrible. Anyways, assuming that sigma equals 1.7 degrees Celsius, test the claim that the population mean is greater than 30.0 degrees Celsius, use a 0.05 significance level, and we are not going to be using the displayed results because we're going to be doing it ourselves. All right, so remember, let's write down some important pieces of information here. All right, so let's see here. We got n equals 61. X bar is going to be 30.377 degrees Celsius. Standard deviation, in this case, is going to be 1.7 degrees Celsius. Now remember, if our sample size is large, 61, which it is, we can say sigma and S are basically the same thing, okay? So now, step 1, let's find our null hypothesis. Well, we're testing mean temperatures, so we know the mean is going to be 30 degrees Celsius. Now, if you're asking where did I get that, let me highlight it for you. So we're going to test the claim that the population mean is greater than 30 degrees Celsius. So our alternative has to be mu is greater than 30 degrees Celsius. Okay? Step 3, let's go ahead and calculate our test statistic. Z equals x bar minus mu all over s divided by the square root of n. So this is going to give us z equals 30.377 minus 30 divided by 1.7 over the square root of 61. And that's going to equal, let's see, I'm coming up with 1.73 to 2 decimal places. Okay, so there's our test statistic. Now, let's go ahead with step 4. Let's draw our graph, label the rejection regions, all that good stuff. So step 4, the alternative hypothesis is greater than, so we know this is a right tail. We know the area in this tail is our level of significance. So alpha is 0.05, which is great. Now remember, due to symmetry, if we looked up 0.05 in our table, remember, we came up with negative 1.96. However, due to symmetry, this is going to be positive 1.96. All right, now if you're wondering where am I getting this number from, I'm going to scroll up really fast. The very first problem we did, notice the rejection region was 0.05. Oh, I'm so glad I looked because I got the wrong number. Negative 1.645. That's what it is. So this is going to be positive 1.645. I was thinking of confidence intervals again. I do that all the time. That's why I use technology. Kind of gets me out of trouble. Now, this is our reject the null. This is our fail to reject the null. Now, if you look at the test statistic that we calculated, 1.73, that is definitely going to be inside of our rejection region. So we kind of write like a nice little sentence. Okay, so here comes our conclusion. So we conclude that since 1.7, what was it again? 1.73 is in our rejection region. And I'm going to state this one a little bit differently here. There is sufficient evidence to indicate that the differences in temperatures is meaningful. Okay, which means that the data that we've collected, so I'm just going to write this here. The data we collected supports the alternative hypothesis that the mean temperature is greater than 30 degrees Celsius. It doesn't mean that the mean temperature is what we calculated it to be, which was 30.377. What it means is the data we've collected is showing evidence that the temperature of the water is actually increasing. Okay? So I hope this helps. Section 3 is going to go by real fast because all we're doing is we're going to be comparing the differences in means. So you got the mean for one group of individuals and the mean of another group of individuals. And we're going to see, is that difference between these two groups, is it meaningful or not? Good luck with this. Take your time. Follow the steps. I'll see you in the next video.